and thanks my Chinese colleagues for the perfect introduction of the laser time transfer. And personally, I have to say I am very, very happy that it is really has been launched to space, and he did confirm the contact and a lot of information taken from our European project. Just my colleagues Roberta Bimbová, Josef Blažej, and Jan Kodek as the co-operator of this project. I will talk very shortly about the improvement of our detector package for the ground segment of the laser time transfer. As you might remember, we are obsessed with stability. Tom Varghese was asking about a huge 1 picosecond over hour. We do present stability of the whole device about 40 femtosecond, about 3 days. And if you do remember Jan Kodet's presentation on laser time transfer, he was showing long-term stabilities of this kind. So I will just show some recent achievements in the ground segment detector for the laser time transfer, and I will spend some time on developing of the INGAS SPAD detector package for very attractive 1 micron wavelengths and detector for good SLR or space debris laser ranging. I will spend some words about, we have developed new circuit to operate this INGAS, commercial INGAS chip for SLR. Okay, back to the laser time transfer detector. I have described it in detail on the previous workshop in Stuttgart. As I mentioned, we are obsessed with stability, so we are just playing with it. The game we have developed a passive compensation trick, how to stabilize the detector so it will have stable delay in different temperatures. And we found we are now stabilizing so well so that the limitation was a comparator used to sense the detector. So we are now playing, one of my students is playing to find out the better comparator. The funny thing is that even the manufacturer is not able to map for us good enough the temperature stability of the comparators they are producing. So we have to install it and see what is the best. And we have found some good candidate, including space qualification and everything, and the overall temperature delay drift, we are well below, we could be well below 100 femto per Kelvin. It was this is the very first result obtained summer this year. It is 150 femto over the whole operational temperature range, but there is still the operational space to improve it well below 100 femto. So this is our improvement for the ground segment of the laser time transfer detectors. Now regarding the 1 micron detector, we are using just like other stations. I think all of them are using the same detection chip. Provided by different companies, but this is the keyword with active area of 80 micron, 3-stage thermoelectrical cooling and stabilizing. Unfortunately, there is an installed window which is transmitting only 1 micron wavelength, which is practical for 1 micron ranging, but it does not allow to use it for different wavelengths, which is INGAS detecting. And its application was pioneered by the French colleagues and Johann Eckel in previous years for lunar laser ranging very successfully. However, our goal was to develop a very compact detector package which would provide millimeter accuracy and picosecond stability for broad range gates and so on. I will show in my talk. And what was necessary to develop a new active quenching and gating circuit to operate this chip. This is the block scheme. I will not go to the detail. The fact is that this is the direct analogy to the control circuit of our silicon-based chips we are using for a long time. And The problem is that for the InGas you do need much higher biases above breakdown, and still you do need very fast delays of the feedback loop to switch off the bias after the breakdown. So we were trying to modify it to get the higher voltage, higher bias above the breakdown. Unfortunately, up to now we were not successful. So what we were doing, we were just optimizing and tuning to the last millivolt everything to get as high as possible. We did not reach our goal of 10 volts, we did reach only 5 volts. I will show the, and it is installed in the standard SPAD package. And some of the results of our operation with our new active quenching circuit for the range gate of 10 microseconds, the relative sensitivity is within the measurement error, absolutely stable. Having the passive quenching circuit used before and people are normally using, which is quite simple. It is nice, but only in this range. And then the sensitivity is falling down. So in our case, it's stable within the whole range gate. This absolute analogy with our detector, our active quenching circuit. The detection delay is stable within units of picosecond over the whole range gate up to the 10 microsecond. With passive, it is somehow stable just within half a microsecond or 1 microsecond range gate, but later on it is going 1 nanosecond, up to 1 nanosecond and later on. So not usable for SLR or even for space debris laser ranging. So it is stable within the entire range gate. Timing jitter, as I mentioned, we did not succeed the top voltage, so the timing jitter is just modest. And we are getting something like 80 picoseconds overall. However, our laser pulse is not very short, so deconvoluting the laser pulse, we are getting single shot jitter, about 52 picoseconds RMS. Okay, this is 8 to 9 millimeters. And all the details are mentioned in this journal paper. And the long-term stability, the people are, especially in time transfer, asking what is the long-term stability, and this was our goal. It's again not too bad, and not as good as with a silicon, but still not bad. And we are getting better than 250 femtoseconds over hours. So even for laser time transfer, it is useful at 1 micron, and for all the measurements and SLR, it is really good and really acceptable. So this is how it looks like. It is a standard housing. Just the optics is missing on the picture, and power supply. Because of tuning everything, we have to control very carefully the temperature to small fraction of degree. To control the biases, again, to very millivolt level. And the key parameters, jitter less than 60, detection probability more than 20% at 1 micron, dark count rate typically below 160, 150 kilohertz. You can gate it, or it's gateable from 100 nano to 10 microseconds, and the signal output is a standard NIM with a very fast fall time to get good timing. And temperature drift is, for our cases, is not very slow, but it is just, we are just on the beginning of the game to reduce it. And the stability in time deviation, as I mentioned, is significantly better than 300 femto per hours. So let's conclude. The K14 SPAD detector package using 100 microns thermoelectrically cooled single stage detector package was optimized, and much better than 200 femto per Kelvin was achieved. We did optimize the in-gas SPAD detector package for SLR with active quenching, and the stability is quite good over the whole usable range gate. The costs of our solution are a little bit increase of single shot jitter. With 10 volts above brake, you can have 30, but the stability is good, and a little bit lower detection probability. And the detector was developed for SLR and space debris. That's all. Thanks for your attention.
Can we hear something from audience?
Hi, Ivan. Thanks a lot for the presentation. Very interesting. Do you see the possibility to slightly modify or use it for other wavelengths, like 1550 nanometers, or just exchanging the chip?
Thanks. Definitely yes. That's why I am so unhappy about the window. And because in-gas, in principle, and we are playing with in-gas 20 years from different manufacturers, but all other chips we have in our labs without any window are working, but they are slow. So if you will be happy with nanosecond jitter, yes, but or another option is the company is selling chips for without coating, without filtering, or chips dedicated for 1.5 micron wavelengths, but dedicated for fibers. It means or fiber is permanently contacted, or there is no fiber, just necked chip, but anyway small, 25 micrometer in diameter. So yes, you can have, and we can control it by that way with all the thing. We can control it, but you are limited to 25 microns. The third option, which is very, but possible, somebody may be willing to do it, is to remove the window. That's possible, but it is not a trivial task, because you have to not remove, you have to replace it and keep renew the vacuum inside. Otherwise. So this is extremely delicate. Yeah.
One last question, Ivan.
Ivan, thank you. Does the band gap support 532? And the other question is, what sort of QE can you get at 1500 nanometer?
You mean with in-gas?
Yeah.
I think the same as at 1 micron.
Okay.
I did not check it with this chip. You know, there are many variants of in-gas, but as far as I know, the classical curves, they are rather flat from 1 micron up to 1.7 or something like that. So plus minus few percent, it should be the same.
And what's the maximum rate at which you can operate this device?
Once again?
What's the maximum rate at which you can operate this device?
You mean gate
yeah,
operation?
Right.
We did not check. You might, even with our circuit, you might use our trick with shortening the gate with the first breakdown and so on. So in principle, many kilohertz. We didn't try. However, you will face a lot of problems with increasing the effective dark count rate. We made this study for Clement with silicon chips some years ago, and so on. So up to 10 kilohertz, I would say it's okay. Above this, it is starting to be delicate. Or what we are preparing now, we are preparing active quenching modification of this circuit without the gate at all. And this is a different story. This is what exactly the Graz group is doing, CW operational SPAD, but this one is rather noisy, so 160 kilohertz is rather noisy for CW operation. So I'm not sure. I can promise you 10K, but above it, we have to play, and definitely it will be some kind of compromise between bias above break, it means speed, photon detection probability, dark count rate, and repetition rate.